In the last video, we saw how resolution can prove whether a sentence is entailed by a knowledge base. We have also shown an example. That's powerful, but it can also be computationally expensive because resolution must explore every possible combination of clauses. We have shown one example where we do with one resolvent, the next clause, but you have to check all possible combinations to make sure you find a null clause. In this video, we'll look at a simpler and faster kind of logic. They are called horn clauses, and horn clauses and will help a specific type of algorithm. There are actually two algorithms, forward chaining and backward chaining. The key ideas behind logic programming languages like Prolog. They drive those logic programming languages. So what are the horn clauses? Let's start with a basic idea. Okay, it's a simpler form of knowledge. So a horn clause is a disjunction of literals with at most one positive literal. At most one. Okay, so that's the important thing. At most one positive literal. So it's a disjunction. So let's say this is an example of a horn clause. Not A, not B, or D. So you can have many negative items, but at most one positive. Okay, so this is a horn clause. So if there is exactly one positive literal, then it's called a definite clause. Okay, exactly one. So horn clause in general has at most one, and definite clause has exactly one. So that's the important part. So if there is no positive literal, then it's called a goal clause, and often used so when we want to prove something false or reach a contradiction. Okay, so it's a goal clause, no positive literal. So horn clauses are special because they are closed under resolution. It's a very important thing. Closed under resolution means when you apply resolution to two horn clauses, what it produces is also a horn clause. So that's what it says, that resolving two horn clauses always gives another horn clause. That's not true for arbitrary CNF formulas. When you take two CNF formula, you cannot guarantee that resolving those two CNF forms or clauses will create a horn clause or CNF clause. So horn clause is definitely much more easier to handle. Horn clauses are special because they're closed under resolution, as I said. So every definite clause can also be written as an implication. Okay, so let's see that. So definite clauses can be written as an implication, and that's kind of the reason they are easy. So if you do the implication elimination inference rule, then so let's say this term L11 and breeze implies B11. If you apply implication elimination on this, this will become not of L11 and breeze or B11 by implication elimination. Okay, so now when you open this up, this becomes not L11 or not breeze by De Morgan or B11. So we have seen that when we have seen the resolution example, and you see this becomes a horn clause because it has at most one positive literal. So this part is called the body. So this part is called the body, and this part is called the head, the conclusion, okay, the fact. So if there is only the head, just if we say, oh, B11, then we actually mean B11 is true. Okay, so the generic format is body implies head. Okay, so A and B implies C. So A and B is body, C is head. Okay, true implies A. So here means the fact is A is true. So this is a very important type. So why horn clauses are so useful? So the horn clauses are so useful because they are simple. They make the inference fast. In a general propositional knowledge base, checking entailment can be exponential. like we said, that all possible combinations, if we have like n number of clauses, then you can have different, to the power n combinations, so which is exponential. But with Horn clauses, we can decide entailment in linear time, in the size of the knowledge base. How? Because that will have those two algorithms which we talked earlier, the forward chaining and backward chaining, and we'll discuss those. So the linear time, so that's because those forward and backward chaining algorithms only make a single pass through each rule and fact. So rule is those implies that, and fact is where there is just one literal and it's true or false. So that's called simply a fact. Okay, so you see that single pass through each rule and fact, never revisiting what's already inferred. So that makes life much easier, computational cost much cheaper. So why Horn clauses matter then? Because simply this is an if-then structure, right? Like this one. So here, if you can interpret this one, is basically means that if there is L11 and breeze, it implies that square 11 is breezy. So that's a simple if-then rule. So it's closed under resolution, which I already said that this is basically when two Horn clauses are resolved, they always give another Horn clause, which is not true for CNF formulas, right? Another thing is that they enable efficient algorithm, okay, that we already said that the forward and backward chaining algorithm they will use, and which only makes a single pass through each rule, and that makes the cost much lower. And it's easy to understand. All of us understand if-then rules much easily for human understanding, but of course computers can interpret much more complicated thing. But for human understanding, if-then is much easier to understand. Okay, so Horn clauses are nothing complicated. They are just if-then kind of rules written for logical understanding, and then remove the implication elimination to convert them in the CNF form, where at most one literal is positive, and if there is exactly one literal positive, then that will be a definite clause.